So thanks again for the introduction, and thank you everybody for coming. I'm very excited to come share some of my thoughts and work with this group. So I'll get right into this. What I was planning to do here, and I'm very happy for this to be interactive. I tried to include a little something for everyone in a diverse audience in a talk like this, but I doubt we'll get through everything I have in the slides. But I was going to try and tell a story in 2 chapters. So the first chapter of the talk is going to be really an overview of the current role of quote unquote causality in air quality regulation. So a very quick overview of how the EPA considers notions of causality in the regulatory decision making, and in particular, how the 2020 review of the National Ambient Air Quality Standards really surfaced some challenges to how the EPA is viewing causality. And the sort of undercurrent of all of this should be the emerging role of what I would call statistical methods for causal inference in this domain. And so the punchline of this first part of the talk is going to be that causal inference methods are becoming more important for the science that underlies these regulatory decisions. So after convincing you all of that, if you didn't already know all of that, the second part of the talk is going to, if we have time, go over 2 specific statistical methodology problems in causal inference. It's not going to be particularly technical, but hopefully it will outline kind of the broad contours of these, what I view as very current statistical methods research problems. One in what we'll call bipartite causal inference with interference, and one that's actually about deep learning. And if you'd asked me about 5 or 6 years ago if I'd ever have deep learning in the title of one of my papers, I would have laughed. But here, here we are. So anyway, the punchline here again, the second chapter is going to be just to outline 2 modern biostatistical methods research problems relevant to this topic. Okay, so I'll start with just a very, very high-level overview of setting national ambient air quality standards. Many of you here probably know more about this than I do, but in case this is not something you're familiar with, the very high-level view of this is the EPA has to answer this question every few years of, do the national ambient air quality standards adequately protect health and welfare? They do this for lots of pollutants. We're going to talk today about the national ambient air quality standards, or the NAAQS for particulate matter, as we'll call PM. So again, the very, very high level view of this is what the EPA does in answering this question is they integrate all of the science, the peer-reviewed literature on some pollutant, PM, then they recommend some policy, and then there's some weigh-in by what's called the Clean Air Scientific Advisory Committee, CASAC, which is an appointed panel of independent experts, essentially. And so they will weigh in on the EPA's integration of the science, and then after that, the EPA makes a decision about the air quality standards. So this is probably familiar to many of you. Here's a flow chart. I didn't put this together. This is flow chart by the EPA. It's a very complicated process. But what I'm talking about here, and where we'll spend most of our time, is kind of in the middle here, where the EPA integrates all of the science. They come up with a policy assessment. There's this iteration through the yellow box, which is the Clean Air Scientific Advisory Committee. I guess I should probably use this pointer instead. The Clean Air Scientific Advisory Committee weighs in on this process, and then at the conclusion of that, there's, that information is output, and there's a series of more steps before the EPA finally makes a decision. So that's the basic. So we'll talk a lot today about what's called the integrated science assessment, which is, here's a very long description of it that is probably impossible to read on the slide, but I'm going to zoom in on just this part down here towards the bottom here. To highlight one key outcome of these integrated science assessments. The EPA integrates all of the science available for, let's say, in this case, PM, and then they make what's written here, what's called a causal determination. So they view the entire weight of evidence supporting whether the degree to which one might believe the association between a particular type of pollutant and a particular health outcome is quote unquote causal. And this is, for our purposes today, going to be one of the main outcomes of this integrated science assessment, this causal determination. So how does the EPA do this? For these causality determinations, they use a 5-level hierarchy that classifies weight of evidence for causation. So it's based on the integration of findings from various lines of evidence. That's all integrated into, I'll underline here, a qualitative statement about the overall weight of evidence in causality. So the EPA takes a particular relationship, say it's the relationship between long-term PM and mortality, or we do this for many other relationships, And they make a determination of one of these 5 categories here. Is it a causal relationship? Is it likely to be a causal relationship? Suggestive, inadequate, not likely, etc. And again, this is a key outcome for this process. And they do this for many different types of outcomes. So here's a table pulled from one of these integrated science assessments that says, well, we're going to talk about fine particulate matter. We're going to talk about all these different health category endpoints, and then we'll talk about short-term and long-term exposures. And each of these elements in this table gets one of these causality determinations. So hopefully that gives an overview for folks who have not are not familiar with this. Okay, so let's talk about what happened when the NACs for PM were reviewed in 2020, which again, folks, many of you may be quite familiar with this. So for the purposes of the discussion today, we're just going to talk about one of these causal determinations for illustration. It's going to be an important one, which is the causal determination between long-term fine particulate matter and mortality. So if we rewind, we're talking about the 2020 NACs consideration. If we rewind to where we were the last time the NACs were revised in 2012, we have this quote from, I forget which EPA document, that says the 2009 ISA reported the evidence was sufficient to conclude that a relationship between long-term PM exposures and mortality is causal. And then this is an important part I want to highlight. The strongest evidence supporting this conclusion was provided by epidemiologic studies. So that was 2009. So that's sort of where we were when the NACs were being revisited in 2020. So we can start to put a timeline here. So in 2009 and then in 2012, there was an integrated science assessment for PM and a NACs revision. When the EPA started to revisit this in advance of the 2020 reconsideration, they produced a draft ISA in 2018. The Clean Air Scientific Advisory Committee reviewed and commented on that in 2019. And then there was the EPA issued their final integrated science assessment for PM. And here's a table from it where we see these relationships similar to the table I showed up before, where I've highlighted the ones we're focusing on for this talk. It said that in terms of short-term exposures of PM 2.5 and mortality, in 2009, we determined it was a causal relationship. And then again, in 2019, the EPA classified it as a causal relationship. And similarly for long-term exposures between PM 2.5 and mortality. So nothing particularly new, or nothing new in terms of the causal determinations when this was revisited in 2018. But then CASAC weighed in on this Clean Air Scientific Advisory Committee. Here's some quotes from their consensus comments. They have to reach consensus on a set of comments that they officially submit. So the CASAC members had varying opinions on whether there's robust and convincing evidence to support the EPA's conclusion that there's a causal relationship between PM 2.5 exposure and mortality. The CASAC did not reach consensus on the causality determination. And some members of the CASAC think that the EPA must better justify their determination. These are sort of key quotes I pulled from those consensus comments. There's one comment in particular from an individual member of CASAC, Tony Cox, who was the chair of CASAC at this time, that I'll highlight here. I think it's worth reading. It says the current draft ISA states major considerations in terms of causal determination categories that make no clear testable or falsifiable predictions. No tests for the predictive validity of the causal determinations are proposed, and no results of the validation tests are reported. In this sense, the causal determinations in the draft ISA are not scientific statements. Those are really fighting words in terms of how the EPA has been doing this. So this is the chair of CASAC who really came out swinging against this whole process for causality determinations. However, other members of CASAC, these are quotes from the same document, other members of CASAC are of the opinion that although uncertainties remain, the evidence supporting the causal relationship between PM 2.5 exposure and mortality is robust, diverse, and convincing. The causality determination was first clearly promulgated in the 2009 ISA with full CASAC support. It was widely accepted by the scientific community and many public health organizations, including the WHO. There is no credible or convincing new evidence since 2019 to question or refute this determination. The evidence supporting a causal relationship is even more robust now than it was in 2009. These are quotes appearing in the exact same document. These are consensus comments, basically saying CASAC does not agree on this. Some members of CASAC don't buy any of it. Some members of CASAC say this evidence of causality is only stronger than it was 10 years ago. Okay, So what happened? So just remind us of the timeline. The EPA had their draft ISA in 2018. It was reviewed by CASAC. We just saw some of their comments. EPA eventually finalized the ISA for PM. And then in December 2020, the administrator made the decision to not change the air quality standard. So even with the ISA concluding a causal relationship between PM 2.5 and mortality, and EPA's another document I'm sort of glancing and referring to called their policy assessment recommending a lowering of the standard, the EPA administrator decided that the current standard protects public health within an adequate margin of safety. The administrator recognized that epidemiologic studies examined associations between distributions of PM 2.5, air quality, and health outcomes, and they did not identify particular PM 2.5 exposures that cause effects. I'm going to pretend they didn't just make a pun there and call them particulate matter exposures. So you can see that essentially the EPA administrator sided with the portion of CASAC that did not buy any of the causality determinations, and in particular, the portion of CASAC that was questioning the evidence from epidemiological studies. Does that make sense, roughly at least? Okay. So that's December 2020. In 2021, we have a different presidential administration, and the Biden administration reopens consideration of the 2020 NAAQS. A new CASAC is appointed, and there's some detail there about that I'll sort of skip over. We can talk about if folks are interested. But there's a new Cleaner Scientific Advisory Committee, and the EPA produced a new document, which they called the supplement to the 2019 PM ISA. And this quote here from the document, the evidence presented, it's worth reading. The evidence presented in the 2019 ISA, that's the original one, along with the targeted identification and evaluation of new scientific information in the draft ISA supplement, provides the scientific basis for the reconsideration of the 2020 PM NAAQS decision. So there's new scientific information that's so important, we have to revisit the decision that had been made in 2020. So in March 2022, this new CASAC made their comments. The EPA is not issued a final decision on this yet. And I was a member of one of the sub-panels of CASAC that weighed in on this. So happy to talk about more than what appears in the slides here. Okay. Where does causal modeling come in? So there's new scientific evidence. That's what the EPA has said. That's why the administration has reopened this consideration. So here are some quotes from a combination, I think, of the draft ISA supplement and the policy assessment in 2021. The draft ISA supplement considers studies that employ causal modeling methods, given that such studies were highlighted by the CASAC and identified in public comments in the 2020 review. So they're saying, if this was a big deal that was raised by the previous CASAC in the 2020 review, we have a bunch of new studies that are using what they call causal modeling methods. Since the completion of the 2019 ISA, numerous US and Canadian epidemiologic studies conducted accountability analysis or employed causal modeling methods to examine both short and long-term PM 2.5 exposure. The studies use a variety of statistical methods to control for confounding bias. They report consistently positive associations. Epidemiologic studies that use causal modeling methods have expanded since the 2020 policy assessment and further inform the causal nature of the relationship between PM and mortality and cardiovascular events. So again, the EP said there's new scientific evidence. It is particularly relevant to the concerns that were raised in the 2020 review. And that, at least some of that evidence relates specifically to the use of what they call causal modeling methods in these epidemiologic studies. So just to give some examples, this is a table pulled from that ISA supplement. I don't know how easy it is to see, but if you study causal inference, you'll recognize some things here. So we have the use of generalized propensity scores with regression calibration, inverse probability weighting, difference in difference analysis. So these were things that were not unheard of in air pollution epidemiology, but they were not, I'd say, particularly prominent before these years, basically, the last handful of years. And now we have them cited specifically as part of the scientific basis for reopening the consideration of that. So what did CASAC have to say about this? This is the new CASAC. So actually, CASAC made several specific comments on the use and the description of what EPA called causal modeling methods, which I wasn't going to go into, but would be happy to chat about. But ultimately, CASAC reached consensus that the standard should be lowered. So all CASAC members agree that the current level of the annual standard is not sufficiently protective of public health and should be lowered. There was not consensus on how much it should be lowered, as indicated by the following two statements, which I won't read, but there was consensus in this new CASAC that it should be lowered. And then this is all still in process, and the EPA has not issued, the administrator has not issued a final action on this. So what am I trying to tell you in this story here? So there's obviously ongoing high-stakes debate about air pollution policy. Previous CASAC has challenged some of the EPA policy recommendations on the basis of the use or the misuse of causal inference. This research community has responded with new research studies that use something that has been referred to as causal modeling. My own opinion on this is that at a minimum, it says that the demand for what a statistician might recognize as causal inference methodology is going up in this domain. And there are some new methods developments required for those of you who are interested in developing statistical methods. And the EPA, I think, has a serious interest in ingesting these types of new studies and these types of new methodologies into their causal determination framework and how they do these integrated science assessments. So I think that's the conclusion of chapter 1. Does anyone have any comments or questions about that as I pause for water? Okay. When should I plan to stop talking? Yeah, please. I mean, it's like literature review plus. So it's like huge literature review. They have their own sort of internal standards for how they decide which studies are more or less important in that literature review, and then they integrate all of that into one of these causality determinations. I mean, they do this over a period of years. And it sort of loosely follows, if you're familiar with sort of standard procedures for a systematic review, it sort of loosely follows, I think, or maybe not loosely follows those standards. But yes, enormous literature review, I would say. I mean, these ISAs are hundreds of pages long. Other questions? Yeah. That's a really good question. That's a very good question. So the most recent CASAC, the chair is a statistician, Ian Shepard, but it's a lot of epidemiologists, clinicians, toxicologists, people from the sort of air quality management community who work for a state or something like that. And I think that's how it's been historically populated. One of the things that was noted in the 2020 CASAC was that I don't think there were any epidemiologists on it. I don't think there were any statisticians on it. Yet there was a lot of discussion about causal inference. But that's a good and perhaps contentious question.
So who chairs?
Who chairs it now?
Shepard.
Leanne Shepard is the current chair of CASAC, yeah, University of Washington. Yeah.
So I'm from Leanne's department,
Right.
And I love her, but at the same time, she definitely had a very clear view on what she believed was correct in terms of air pollution policy.
Yeah.
Before she was the chair. So I'm wondering like how political standing biases are taken into account at all.
I mean, that's a really big question, I think. So repeat the question. Yeah. So if I get it right, correct me if I paraphrase your question wrong, is that individual members of CASAC might have preconceived ideas, beliefs, opinions on the role of pollution and regulation. And is that separated, or how could that be separated from how they weigh in on this process? Is that an appropriate paraphrasing? And it's a really good question. I don't know the answer to that question, but I guess what I would say to it is these are supposed to be experts. They should have opinions on this. They're scientific opinions. And CASAC, in my experience, in watching and participating in one of their ad hoc subpanels, takes very seriously the sort of where the support in the scientific evidence is for whatever that opinion is. I guess that's my response to that. But it is absolutely correct to view, I mean, I don't think I'm being too cynical to say that it is absolutely correct to view the members of the Case Act and their backgrounds and what their sort of, I'd say, political but not scientific biases might be. Other questions on this? What's that? Oh. Oh, okay. Will you let me know if there's something in the chat I should respond to? Thank you. Okay, thank you. All right. So we can talk about biostatistical methods now, if that's okay. So this is just meant to mostly be background. And what I'll talk about now is, if you have time, to go through two causal inference methodology problems. One is what I'll call bipartite causal inference with interference. I was not intending for this to be particularly technical, but if you are working in statistical methods, hopefully you'll understand where this is all going. And if you're not working in statistical methods, hopefully you'll understand sort of the point of why we're doing it. That's my goal. So let's see here. Thank you very much. Uh-oh. Thank you. Okay. Yeah. Great. Oh, yes, thank you. Thank you. All right, so I want to highlight at the outset, this was something that, I want to highlight at the outset that there's a difference between asking a question about the effects or the causal effects of pollution exposure and asking questions about the effectiveness or the causal effects of interventions to reduce pollution. So those are different questions. And so the first question is something that might generically be posed: what is the causal effect of exposure to PM 2.5? This is really a question about exposure response estimation. We want to estimate some exposure response relationship between an exposure and some health outcome. This is a large focus of the ISAs. They have to come up with those causality determinations to answer questions like this, essentially. But there's no question about an intervention here, right? If we could understand this perfectly, then our answer to this question might imply what would happen if we intervene to reduce air pollution. But there's no direct consideration of an intervention or an action in this type of question. The second question I have here, again posed generically, is what is the causal effect of some intervention that was done or might be done to reduce exposure to PM 2.5? So hopefully you can see that this is a different question. This is a question that is more directly tied to some specific regulatory action, right? The EPA has to decide about a regulation, but then what actually happens where the rubber hits the road is there's some intervention done on some source of pollution. And so I'll refer to this as a more source-oriented question, which is something that I'll come back to at the end. But then we have the answer to this question might indicate intended consequences of this action, unintended consequences of this action, co-benefits, co-harms, et cetera, things like this. But the main point that I want to make here is that the types of methodologies we might use to answer these two different questions are different, or might be different. Okay, so just to be a little bit more specific here, I'll introduce a case study about coal-fired power plants. So there are lots of regulations that end up impacting the emissions from coal-fired power plants. And so in response to some of those regulations, this is a picture of a coal-fired power plant. Lots of stuff comes out of a coal-fired plant smokestack. Never mind the fact that I've labeled the steam there. I know that, but lots of stuff comes out of a smokestack when coal is combusted. And in response to regulations, one thing that is commonly done on coal-fired power plants is they install what's called a flue gas desulfurization scrubber, a scrubber that you can think of as literally scrubbing the sulfur dioxide emissions that come out when coal is combusted. Okay, so we know that when we put one of those things on there, we reduce the SO2 emissions that come out of that smokestack. What we also know is that reducing SO2 emissions will reduce the ambient air quality. Because what happens is when SO2 comes out of the smokestack of a coal power plant, it starts to blow around in the atmosphere, react with other things in the atmosphere, and it forms into those particles. There are surely others who know much more about this than I do, but this is the broad contours of how this works. That's called secondary formation of PM 2.5. And so this stuff blows, or basically it blows all around in the atmosphere, you can think of, once it comes out of the power plant. So we reduce the SO2 emissions, we should reduce the ambient particulate pollution, and then we know that should confer some health benefit, because we know the ambient PM is bad. But in terms of a specific question we'll try and answer just for this case study, it's, do scrubbers on coal-fired power plants causally affect the hospitalization for ischemic heart disease among Medicare beneficiaries. So just sort of fix your mind on that as an example question. So this is where I had I failed to get my animation to work. But what would be seen in this black square there, if I not failed to get my animation work, is an image of basically the whole eastern United States from like the Mississippi River east, and a dot representing one power plant outside of Atlanta. And then these bursts of dots coming out of that dot and moving all over the East Coast, up and down, depending on the season. So it's a cartoon animation of these bursts of dots emanating from one point in space, which is a power plant, and blowing all the way up to Maine, all the way down to Florida. And you can see how these plumes, so to speak, move in time and space. And what that cartoon was meant to illustrate was that emissions originating at the power plant, they move, and they move quite long distances. They really do move from Atlanta to Boston and further. Which means if we intervene to reduce the emissions at one point in space, at one power plant, there should be some impact on the ambient air quality and then the health across a very large spatial area. That's really the main point that I want to convey. That's just long-range pollution transports, the people who study air pollution. Right? What it's going to lead to from a statistical perspective is a challenge of making inference on what we'll call a network of interconnected power plants and population locations. And this is called in causal inference with interference. So we'll talk a little bit more about that. And so I want to just pause and again draw another distinction with sort of environmental health literature here, environmental engineering literature, exposure science literature, is if we want to learn, as the title of the slide says, something about the effects of specific pollution sources, that you can sort of, again, very roughly sort methodologies into two categories here. There's what I'll call receptor-oriented methods. This is basically source apportionment, which basically means we go to a location, we measure the chemicals that are out there in the air, and then we kind of back out what types of source those chemicals came from. So we might be able to answer the question about what's the effect of exposure to pollution that has a chemical signature of coal combustion. Hopefully that's an appropriate characterization of these methods for people who are more expert in it than I am. But there's no intervention here, right? We just sort of learn coal pollution looks kind of like this chemically. We can look in the places where we identify those chemical signatures and see if that pollution seems to be, say, more harmful than pollution with a different chemical signature. So I'll call those receptor-oriented methods. But again, the main point is you start at the place where you measure the pollution and you kind of work backwards to find what type of source that pollution might have come from. What I'm going to focus on again is this term source-oriented methods, which is to say, well, we're actually interested in a set of specific point sources, these power plants. Some of them put these scrubbers on, some of them didn't. And we want to know the effect of that. And so we want to answer a question that's more like, what's the effect of intervening at a specific point source of pollution, a power plant? And this is where I think that there was a lot of sort of room for new statistical methods to develop. So this, we published published some papers with this buzzword bipartite causal inference with interference, but this is really what it is. It's saying we want to evaluate the causal effect of an intervention. Say it's a binary intervention. The scrubber is there or it's not. And we have these two features. One is what we call the bipartite structure, which is to say the intervention we're interested in is designed on one type of observational unit. Here it's a coal plant. It's intervened upon or it's not. But then the outcomes that we're interested in are going to be defined on some other type of observational unit. So here it's going to be zip codes where we'll have the hospitalization rate. So the zip codes are not treated with the scrubber. The power plants are treated with the scrubber. But the power plants don't have hospitalization rates. The zip codes have zip code hospitalization rates. There's nothing particularly unique about this bipartite structure. This comes up all the time. But what is, I think, a little bit more unique in this is the notion that I alluded to before called interference, which is that there's some interconnectedness between these two different types of units, the power plants and zip codes. That means the outcomes of any particular zip code are going to depend on the treatments at multiple power plants. That's what it would mean in the context of this problem. So I wasn't going to go into much detail about potential outcomes notation and everything here. It gets pretty dry. But the basic idea I want to convey here, just to give an appreciation for those of you who maybe are not used to thinking about potential outcomes, to give an appreciation for how this becomes a difficult problem pretty quickly. is the sort of standard setting for potential outcomes relies on the assumption of no interference of the stable unit treatment value assumption. And what that says, that assumption says, is if I want to talk about the potential outcome for a given location I, this notation here indicates that that potential outcome might depend on the treatments applied to all of the power plants. What the stable unit treatment value assumption says, it doesn't. It says that it doesn't actually depend on all of the power plants. It just depends on the ith power plant. So I'm skipping over some detail here, but this is an assumption that does a lot of heavy lifting. If you're not used to thinking about potential outcomes, but you've heard about them before, read about them before, this is where we get this idea that there's two potential outcomes for each unit. What would happen if it were treated and what would not happen? What would happen if it were not treated? The fact that there's two is a consequence of this stable unit treatment value assumption. In this bipartite interference setting, we're not going to make the stable unit treatment value assumption. We're going to, at least to start, say that, well, this potential outcome at the ith location, the ischemic heart disease rate, does actually depend on the treatment status for all the power plants in the country, of which, say, there are J. So now we've gone from having two potential outcomes for every location to having 2 to the power J potential outcomes for every location. That's a lot of potential outcomes. And so this clearly complicates things in a way that requires a lot to do. And so again, the point here is that I'm trying to convey, again, it's just that this becomes a complicated problem fast if we want to acknowledge long-range pollution transport in this way. So in case there are any of you who have read about, thought about, or worked on causal inference with interference, there is a difference here than where most of this literature is that I also want to highlight here. So the most common settings for methods development in causal inference with interference are infectious diseases and social networks. The idea with, say, infectious disease is that if I get vaccinated, then the members of my family are less likely to get infected. Therefore, their outcomes depend on their treatments, but also on my treatment. That's like the classical example of interference where outcomes for a unit depend on the treatments of a bunch of other units. And so this, these most common settings, the interference is usually there because of some dependency in the outcomes, unit to unit outcome dependency. If I get infected, I'm more likely to infect somebody else, our outcomes are dependent. It's really different from the underlying phenomenon giving rise to interference in this air pollution case, which is one that I call complex exposure dependency, where the interference is dictated by this underlying physical chemical process of how sulfur dioxide converts to sulfate and sort of moves around in time and space. It's really more like a treatment diffusion type problem. And this might be more aptly described as a physical or geographical interference. And then I have this quote, just to be clear, for those who are thinking about interference for the first time, this quote from this 10-year-old paper by Checkin and Vanderweel that says, interference is not simply a problem that needs to be addressed, it gives rise to new causal quantities of interest. So I just want to, it's not like something you adjust for in the way you might adjust for a spatial correlation in your analysis. It really does introduce new questions and new things you might want to estimate. And so hopefully I'll give a flavor for that. So just to outline kind of, this is several years worth of methods development we've been working on to bipartite causal inference with interference. There's kind of 3 tasks that I'll say a few words about each. One is we need to obtain what's sometimes called an interference mapping. This is some way to describe how the outcomes at any particular location depend on upwind power plants. We can sort of think of it that way. We're going to organize this data into an adjacency matrix. This might be called a source receptor matrix in air pollution. So that's sort of task number 1. We have to figure out a way to learn how a power plant at a given location impacts a zip code at a different location. Once we do that, we have to do a lot of work to specify potential outcomes and causal estimands that are of interest for this type of problem. What I'll outline briefly is 2 estimands that correspond to, one corresponds to the effects of local interventions. If you follow this literature, this is something more like a direct effect. And another estimand that would correspond to upwind interventions. And this is something more like a spillover effect if you follow this literature. So there's a lot of work and assumptions that go into defining those estimands. And then we have to have a procedure for estimation. And this turns into estimation on a network, which is not a particularly simple topic. And we've got kind of 2 strategies ongoing to do this, one based on generalized propensity scores and one based on Bayesian additive regression trees. So the first step is to obtain the interference mapping, which is this matrix that says how much does the jth power plant impact the ith zip code, this is what would be called the source receptor matrix. I'm sorry, speeding through some of this. So we've explored two different types of approaches to do this. One is sort of a purely statistical approach, which says, well, we've got lots of data on power plant emissions, ambient pollution, wind vectors, et cetera, et cetera. We should be able to estimate how this air pollution moves through space and how, emissions from one power plant impact the zip code over here. An engineer will think you're crazy if you tell them they're going to do that with statistics. It's happened to me many times. But we've got some methods development there. If folks are interested, you can just sort of read the keywords of those paper titles in terms of how those methods have looked. The other approach, and actually we've been doing this one for longer, is to take this more engineering approach. And we developed what's called a reduced complexity air quality model to do that. It's called PIAGS. The key reference is sitting there. And what was going to be on the bottom of this slide was that same cartoon I tried to describe before. And so you've got these sort of plumes of emissions and they're moving over time in space. That's what this reduced complexity air quality model does. It's a computational model. So that's step one. Step two is we then specify potential outcomes in causal estimands. I'm wondering if I should just kind of skip past this, which I will do, and try and give a sense of what this looks like when we do it. And then we have this procedure for a joint propensity score analysis, where at this point in the development, the method doesn't look that different from how propensity score methods have been used previously. I'm happy to come back to this if folks want to talk about it, but I think I'd rather give a flavor of what happens when we do this. So the case study I started with coal power plants is we were dealing with 2005 when sulfate was a much bigger problem. There were 472 coal-fired power plants in the US, and we wanted to know how interventions at those dots impacted the Medicare ischemic heart disease hospitalizations at 25,000 zip codes in the eastern US mostly. And so that's the big there. We have lots of other covariates available for adjustment in this type of analysis. So we sort of decomposed the slide I skipped says that we decomposed this very complicated function of all the treatments into two things. For a given zip code, we define whether the power plant that influences that power plant the most, according to this atmospheric model, had a scrubber. And that's defined as Z. Those are the yellow zip codes here. So if it's yellow, it means that the power plant that influenced that zip code the most had a scrubber, was treated. And then the other part of this problem is what we defined as this basically sort of atmospheric model weighted upwind treatment rate, which we denoted with G, and that's what's mapped here. So the brighter colors here are zip codes where more of their quote unquote upwind power plants were treated. Where upwind is completely determined, I put it in quotes there, but it's completely determined by that air pollution model, that reduced complexity model. So once we get to this point, we can sort of estimate causal effects corresponding to these two quantities, the upwind treatments and then something that's more like the local treatments, what's happening at the power plant that influences this location the most. And we see stuff like this. The y-axis here corresponds to ischemic heart disease hospitalization rates. The x-axis of these two plots correspond to the upwind treatment rate. And the fact that these things are sloping downward like this tells us that as there are more scrubbers installed upwind of a location, the ischemic heart disease hospitalization rate goes down. That's what this means. So I skipped over a lot of that, but hopefully that gives a flavor of why it's sort of a challenging methods problem and what it looks like when we go and do it with these types of data sets. But again, this is the sort of motivating here is motivating premise here is that we're interested in estimating the causal effects of specific intervention sources. And that is the question that I think was a little bit different from what was kind of the most traditional air pollution epi question, at least going into like the ISAs. And we needed a way to account for long-range pollution transport. And it led to all of these other methods developments. So I'll just outline very quickly, since I already promised deep learning and I wouldn't want it to be a shallow talk, I have to outline a little bit what's going on here, which is an application, a fairly straightforward application of deep learning to a problem of non-local confounding. So let me just motivate what we're talking about here, and then I'll sort of skip over the details of this. The motivating problem here I put as adjusting for weather in the meteorology and the analysis of pollution and public health. This is something that comes up in those ISAs about a source of uncertainty in estimating these long-term health effects. So we know that meteorology has a role in what happens to emissions. We know it has a role in what happens to pollution. We know it has a role in what happens to health. And so there's a lot of potential for confounding due to meteorology as a result of these sort of known relationships. And sort of we know this as a scientific community. But typical analysis, not all, but typical analyses, when they adjust for weather in their, say, epidemiological model, they adjust for it locally. They adjust for the measure at the zip code where a person lives. But can meteorology really be characterized by measurements at like a point location? So perhaps not. We know meteorology is this complex spatial atmospheric process. And so we have a different case study, a couple of different case studies here, which I'll sort of skip over. One is sort of analogous to the one I just talked about with coal-fired power plants, where we have emissions controls for NOx emissions in solid power plants, and we want to know the impact on ambient ozone. We know meteorology is important for this process and sort of how to adjust for it. So that's one case study. Another motivating case study of this is estimating the climate penalty or meteorologic detrending, and that's a type of problem where we have some long-term time series of some type of pollutant, and we want to know, and this is sulfate. So it's going down a lot over time. This is actually, yeah, sulfate, essentially. It's going down over time, and we want to know how much of that reduction over time is due to regulations, emissions reductions, and how much of it might be due to sort of long-term trends in climate, in meteorology. So this is another question that people ask, and both of these have the same key question at the bottom, which is, well, how are we going to adjust for the meteorology in a problem like this? And so we have a lot of good meteorology covariates, often measured at dense grids like this across the globe or across North America. So we're going to make good use of these types of gridded spatial atmospheric data sets. So in a cartoonish form, the problem we're trying to solve is, say, we have sort of what I'll call a standard method that adjusts for local information. So we're not really literally going to fit a regression model that looks like this, but just to give the idea, we want the outcome is pollution, the exposure we're interested in is emissions. We'll measure them at location S, and we're going to adjust for the weather at location S, or maybe some complicated function of the weather at location S. And this is what I'll refer to as local meteorology adjustment. What we're trying to do here is to say, well, we think that the air pollution or the health at a given location S depends on the weather at location S, but also on the weather at other locations, S prime, S prime prime, S prime prime prime, dot, dot, dot. And so if we think that there might be confounding due to weather at some other locations other than just S, that's going to introduce this notion of what we'll call non-local confounding, and we're going to use a particular deep learning architecture to account for this. So I'll sort of skip over this and try and explain what we mean by non-local confounding. So at the top of the slide, we would have just as the standard formulation of a no unmeasured confounding assumption ignorability. It says, if we condition on the right quantities L, then the treatment A is independent of the potential outcomes. That's no unmeasured confounding. The typical case says whatever L is that we need to condition on, I skipped over notation, but it's XS, that is, its covariance only measured at that location, X. That would be the standard formulation of this. What we're going to define as non-local confounding, and bear with me, since I skipped the notation slide. For non-local confounding, we'll say, well, there's some neighborhood of locations around us. Neighborhood meant to be sort of a general term. So there's some neighborhood of a collection of locations around S, such that those L's we need to adjust for confounding actually consist of all of those covariates measured at all those points in the neighborhood. So hopefully that it at least makes a little bit of sense. So the question, here's a picture of it here, which I think is sort of clearer, is that we have a treatment at location S and an outcome at location S, and both those things depend on the covariates at location S. That would be local confounding. And we have this problem of non-local confounding, where the treatment and outcome at location S depend on the covariates at location S, and then the covariates at some other location S prime. So we'll sort of skip through this. The idea that we did was to use this neural network technology called UNet, which if anyone here studies neural networks, this is like ancient, 2015 in the neural network literature. So this was an established thing. It was originally developed for biomedical imaging segmentation. But it turned out to be really good for this, because what it does is it takes an input grid of covariates. It's this convolutional neural network architecture that transforms that grid of covariates into what's called a latent representation Z, which will encode a lot of long-range information in that original input space. That's sort of the language you use to describe this. I'll skip over sort of how this works. We have a couple of different ways that we propose to do this type of thing, where we're going to learn for every location what complicated function of surrounding meteorology is important for confounding. That's really what we're doing here. And I think this is, I'll just sort of show this and then I'll close out here. Because I think this gives the idea of what we're trying to do. What we have along the x-axis here is a radius. So you think of this neighborhood. How wide is this neighborhood around a location that's relevant? And what we have plotted on the y-axis is the percent of information, the percent of variance that's explained in a neighborhood around of that size of radius. So if we look here at the purple triangles, it goes all the way up here. We say at a radius of 0, that is only locally, the local covariates explain 100% of the local information. So that's good. That's what we should do. But what happens is if you follow these purple triangles, they go down pretty fast here. By the time we get out to a 300-kilometer radius, the local information only explains about 75% of the variance of weather, meteorology in this case, at a 300-kilometer radius. So that also makes sense, right? Local information should explain some of what's going around in the neighborhood, but we wouldn't expect it to explain a lot of it. I'll contrast that with these blue X's. This is sort of the proposal here, which was based off this thing we called weather to that. It says at very local scales, we sacrifice some ability to explain what's going on at small radii. But we say we get out here to 300 kilometers and this sort of scalar valued, or not scalar, vector valued, but low dimensional summary still explain at every location, defined for every location, explains 95% of the variability in the weather at a 300-kilometer radius. So it captured some of this long-range relationships, these long-range relationships of these weather covariates. So that's success. That's what we were trying to do here to adjust for non-local confounding. And then I have a couple of case studies that were really more proof of concept case studies, and in both cases, they indicated that the method did exactly what we thought it should do. And so again, I'm happy to say more about that if folks are interested. But anyway, the motivating problem for this second methods project was that there are lots of environmental science and epidemiology problems where we're worried about non-local confounding by weather or other atmospheric processes. That's a common setting. In an abstracted from that setting, the more general method setting, we have treatments and outcomes that are measured on spatial units, and we have a dense grid of those atmospheric covariates. The goal is to estimate causal effects of some treatment and some outcome adjusting for confounding. And the challenge is the presence of this non-local confounding. There are treatments and outcomes at a given location might depend on this neighborhood information in the spatial process here. And so we propose a deep learning approach based on representation learning to do this. All right, so that's basically it. So again, the sort of main takeaways here that I'm aiming for is there's an increasing focus on causal inference methods. The use or the misuse of causal inference has become a prominent discussion point in air pollution policy debates. There are many, many new studies that are employing quote unquote causal modeling methods. I didn't say what causal modeling methods are, but that's the language the EPA uses or used in their draft ISA supplement. And so there are these ongoing questions about how can causal inference methods be adapted in service of this EPA framework for causality determinations. And then in terms of two new statistical methods problems, I outlined some work in bipartite causal inference with interference and deep learning for non-local confounding. There are many other methods challenges out there that need people working on them. And I'm over my time, so thank you. There are some references if folks want to have a look at some of the things cited in this talk. So thank you very much for your time.
Yeah, I mean, I think it's an incredibly important question, right? So we sort of heard a lot about how the CASE Act, depending on the political climate, uses these notions of, is it really causal or not to either use the science or not. I think that these causal methods are incredibly exciting. I think that they're very interesting and very important. I think that they bring a lot of benefits to them. So, I think we've heard, right, exactly how they remove a lot of the black box aspects of what we do. And so I think that they're more appealing to people like Tony Cox, who can directly see what it's answering. I think that many of the new causal methods also have really nice ways of looking at the balance of confounders. So we heard a bit about, Cory was talking about, the propensity scores and things like that. And what it allows you to do is really see how well your pseudo populations are matched. So it mimics that RCT, and people can say, oh yeah, I can see based on these measured confounders that they look good. Now that said, I think that we have to be really cautious about saying like, okay, well, now that we have these new methods, right, we're going to throw away all of the original research because we have 30 years of epidemiologic evidence, right, trying to look at these relationships. And those epi methods, right, are trying to get at causality. They're not trying to look at association. That's not the goal, right? They're trying to use those methods to look at it. And also they're often using the same underlying data. So even though there are these causal methods being used, right, they still have the same problems if the data is flawed. If they're using administrative records that have patterning by, in the errors by place that track air pollution, if there's selection biases, there's still the same issues. So super excited about the causal models. I think that there's a strong role for them, but I would still very much say it would be a mistake. And actually, Cory has a beautiful paper on this topic with Francesca Dvonch about, you don't want to throw away all of the original epi methods just because we have some new nice causal models.
Rob, anything to add?
Yeah, well, I think what I would call the Neyman-Rubin causal model, which is sort of the fundamental thing that Cory talked about in his paper, is terrific as a conceptual basis for causal inference. So I think it's very useful conceptually for clarifying the assumptions you actually have to make and also defining the causal effect in a clear way. So when I teach my course on design, I use that model. So I think that's been extremely useful. So I want to say on the propensity score paper that came out in 1983, and there's a special issue of observational studies that's 30 years from the initial Rosenbaum-Rubin paper that's coming out, an observational study. I had a paper on that, and there's also going to be a discussion in the joint statistical meetings about that anniversary. From a personal point of view, I was actually working with both Rosenbaum and Rubin when that paper was being reviewed. So actually at EPA, interestingly. So I feel a personal connection. I didn't do anything with Paul Rosenbaum that was nearly as important as that paper was. Yeah. Rosenbaum later on has a book and has done tremendous work on some of the other topics that we're going to talk about later.
Mm-hmm. So Tim,
yeah, actually, before I comment, full disclosure, I'm not a biostatistician. I'm not an epidemiologist. So you might ask, what am I doing sitting up here? And that would be a fair question.
that's what we need.
I would classify myself as an exposure scientist with background and experience in assessing exposure. So I'm one of those folks that's out there in the field with monitors, putting them on persons, setting up area monitors, and so forth. And so, my comment to this question is a bit more general, not specific to causal inference, but to all of the subsequent analyses. I'm one of the people that appreciates, like Sarah said, it's still the biggest challenge is the quality of the input that's available to go into these models. And it still remains to be quite flawed, to be honest. I'll give one quick example. Cory's talking about all the great work done around spatial and temporal approaches and ways to account for things, various confounders and so forth. All of these 30 years of epidemiological studies that have been done have relied upon, because it's the only data that's been there, are these air quality monitoring sites that have been located for the purpose of regulatory compliance. not for exposure assessment.
Mhm.
So right off the bat, there's flaws with the data from an exposure assessment perspective.
Mhm. So moving on. Corey, anything to add?
I mean, yeah, Sarah, I'm glad you mentioned this because I don't want to give the impression, in fact, the current iteration of CASAC and the PM panel, we had some consensus comments on this. I don't think we want a world with a dichotomy where a method is causal or it's not. I think there are people who want that world. I'm not one of them. The current iteration of CASAC did not consist of any of those people who want that world. And that the point, and so in the statistical literature, maybe that means something, right? If you're reading statistical terms, this is a causal inference method, or this is something that you wouldn't call a causal inference method. But we should not be looking at studies and say, well, was it a causal method or was it not a causal method? And we actually advised GPA to sort of change their language around that. Because there's no definition of what a causal modeling analysis is. And so I just want to be clear, even though professionally I might stand to benefit if every analysis had to use causal inference method, that's not the world we want to be in for basically all the reasons Sarah mentioned. And that there are specific things that something that a statistician would call a causal inference method can help to clarify. And there's an opportunity, as you said, Robert, to be explicit about that with something like potential outcomes, checking covariate balance. And some of these studies do that. Some of these causal modeling studies do that in a way that can be very productive for this. Some of these studies come out, they're causal because the author said so. If there's not really anything specific in them that would indicate what exactly is the threat to validity that this methodology is supposed to address. So I think that's where we need to kind of hone in a little bit. If we're going to use these methods and call them causal, I think it's our responsibility to say, this is the thing that we're trying to fix that maybe a non-causal method would struggle to fix. And some of those studies in the literature do that well, and some of them, I think, do that less well.
Yeah, learning and investigating the causality is not an easy task, and especially with the data collected. Most of the situation, for example, in the causal inference, we have the assumption about no unmarried confounder. So that actually comes up with our next question. How do we handle the potential unmarried confounders in the study design or in the analysis? Okay, so we'll go with first Rod. Rod is expert in causal inference.
Well, I think dealing with unmeasured confounders in the analysis is a very difficult thing to do, simply because of lack of information. So probably the best thing I would say is to try and design studies where you don't have any unmeasured. so the confounders that are thought to be the key ones are actually measured. So I think it's a very difficult area, and I mean, Paul Rosenbaum has a book on this, and he's done great work in this area. It's not really an area where I work more on non-ignorable non-response, which is kind of a related issue, but not really quite the same. You know, I think some form of sensitivity analysis is probably the best way to address it. And, I'd be rather distrustful of methods that make strong assumptions. We're going to talk a little about instrumental variables later, which might be one potential approach, but whether we actually have good instrumental variables is a question.
So Sarah, how do you view this as an epidemiologist?
Yeah, I mean, right. I think Rod had it exactly right. It's incredibly difficult to deal with something that you have not measured, right? If you truly did have an RCT, which many of these tried to mimic, you hope that just by balance, right, by randomizing, you would get rid of unmeasured confounding. But even though they look like RCTs often, right, you're not able to have that same property. You know, the methods that I see people using to try and cope with this are you take those extremes and you do simulation studies. What if there was a confounder that was associated with my exposure with this magnitude and had an effect on my outcome of this magnitude? You know, how much would it sway my answer? Or there's sort of like, you know, a bit of an inverse, which is like, you know, these e-value approaches that people are using of, you know, how big would the confounder have to be in order to see, you know, a biased association of this magnitude. But otherwise, I mean, unmeasured confounding is a real challenge. We hope we get it right.
Yeah, the design is very important, and also like for example, Tim, when you are collecting the data in your team, and we actually are relying on you to collect more rich data, everything.
No pressure.
I felt the pressure before you made the statement.
Yeah, Tim and I, we actually are long-term collaborators, so we have many works together. We need all the excellent data from you. All right, so we'll move on to the next one. So how about the weight of the evidence of causality determinations? Are they useful for forming regulations? Can the framework be improved? You think this is pretty general?
Yeah, well, it's kind of words, isn't it? I mean, and of course, it's hard to separate politics from the words when the words are kind of somewhat, or wishy-washy, which is probably by necessity. I'm not sure how you make it precise, but so it's kind of a tricky thing. I was kind of Cory. He knows that there was a National Academy study that actually looked at this work. It was chaired by Liz Stewart. That I reviewed for the National Academy, and I think they sort of generally came to the conclusion that it was. Well, they couldn't come up with good alternatives. That way. I mean, I think you can always pick holes in the way people are doing things, and so I think they did pick some holes, and they were certainly enthusiastic about the new sort of the causal inference methods, for example. Since there were statisticians on that panel, but I don't know how you would change the way they're going about it personally. So I guess you're doing the best you can in a very imperfect world.
Yeah. Certainly. All right.
I mean, yeah, I knew that panel was happening, and I know that from Chase Act's perspective, I guess I can't tell whether anybody was surprised that this whole causal determination framework came under attack in 2020. Because they've been doing it that way for a while. That had been sort of accepted and vetted as a productive way to do this. And then that whole framework was arguably outside the scope of the Case Act, but that whole framework got kind of chiseled away at in that 2020 Case Act. And so that's what prompted.
I suppose you could try and embed some of this causal, like the definition of a causal effect, for example, might be incorporated more explicitly into the language.
Yeah, and
which could be, from a statistic point of view, I think would be good.
Could be helpful, yeah. And I think, and so, yeah, I've not seen this report. I don't think this National Academy's report has been released.
No, I don't think it has.
So, yeah, I mean, from Case Act's, the current Case Act's perspective, I think there was a lot. It's difficult because I don't think anybody basically what Rod said. I don't think anybody wanted to plant the flag that this is the very best way that we should do this. It was a little bit more, at least I'm just stating my opinion, of the view that well, this is integrating all of the science and coming up with a judgment that we need to use to offer advice to the EPA. I don't really see what else we can do. All we can do is improve this framework. So I'll be curious to see what exactly that National Academy's panel came up with.
Yeah, I'm just curious. Do you think the previous Case Act started to attack the framework because of their own pre-existing political biases and who put them on Case Act? And can you repeat that?
Yes. Do I have to? I did the previous Case Act attack this framework because of their own political biases that maybe were rooted on who appointed them. Is that appropriate? That was the question. I don't know if anybody else wants to answer that question, or if anyone has anything on it.
I don't know so much in the environmental area. In the medical area, of course, there are these attempts to try and codify qualities of studies, right? So there are groups that have tried to randomize clinical trials versus just various types of observational designs. I wonder if that's happened in the environmental area, because I imagine that kind of a way of trying to distinguish between strong and weak studies could be useful in the environmental area as well, I would imagine.
Right.
Not too many randomized trials in
Yeah. I mean, I know those frameworks are used a lot in other testing.
Yeah.
Exposures. I'm not sure they're kind of baked into what EPA does, I think,
Yeah.
for PM, but it's not as explicit, those
Yeah.
like different review things as it is for like other toxic chemicals.
Sarah?
Yeah, I mean, we can't get in the heads of everybody else, right? But I think another thing that happened during the same time frame was a push towards this open science, where there was an effort to try and exclude any studies from review for EPA standards if you couldn't have the data set be available to all. So I think that there was, in general, during that time frame, a movement to try and make smaller the literature that can inform the science. Now, why they did that, everybody is welcome to speculate on their own.
Doesn't require that much speculation.
But I think it was part of a larger movement that looked at causality and what's defined causality, and therefore can we include them when we're considering the ISA and the standard setting.
That's an interesting point, because access to studies is big in the medical world, actually.
Yeah.
It could be big in the environmental world.
Yeah, and I mean, it really, on the one hand, the access that, is an incredibly noble goal, right? I mean, actually, our data set should be available and should be able to be analyzed, and that has many benefits. But there's also restrictions, right? So we are barred with being stewards of these data sets and people's protections. And so many of these studies are unable to actually release the data. And especially because many of the things we're interested in are spatially identifiable and linked to the people and their health records, right? You worry even more about disclosing individual people. So it is right. I mean, on the one hand, you hear it like open science is great. Yes, absolutely, we want open science, but there are limitations that make it challenging.
I mean, the members of the 680 study signed and consented. They're not allowed to share them. And the people who are advocating for making data available, they know that, and so they want to disqualify.
And there was a lawsuit actually as well.
Harvard's not going to give that data up. They're not allowed to. They're protecting the participants.
Yeah, I'll just comment on the original question. Where things were just a couple of years ago. It was a really short time period, and the challenges to the review process and the committee membership. I just want to say I'm thrilled that here we are back to talking about the nuances of causal inference modeling, which is exactly what where we should be, and not lost in where things were just a couple of years ago.
Thank you. So we actually have. Oh, sorry. Go ahead.
I guess I was wondering if you have any insights about maybe sort of like advisory boards or other decision-making bodies that are having the outside of our hospital that are having similar conversations about weighing causal evidence in making decisions. Or
I can't think of an explicit parallel myself.
Well, I mean, you'd have to think, for example, like Arnold Monto headed the vaccine advisory board to the FDA for COVID. And you have to imagine that they're weighing all of the evidence and the epi studies and deciding whether or not the data is good enough. I mean, certainly with the children, right, that vaccine took so much longer. They were sort of weighing the perceived harms, right, versus the benefits, and how good was the evidence. So I mean, I think it's
right, because I'm thinking immediately when I thought about now the body was like, if the standard is an RCT, how do these causal evidence compare, right? Because in our field, RCTs aren't common, so causal evidence sort of common sort of is like more gold standard. I mean, not perfect, but sort of right. It's a different type.
Yeah.
So that's really what I'm sharing.
So I guess I can think of a couple things. So in other areas of environmental exposure, so is it Iowa that does their carcinogen ranking? So that's similar things are going on there. They have to make that decision. Right? Somebody has to decide that this is not a possible or likely percent. And the other thing in terms of, again, I don't know if it's a great parallel, but at least as I understand it, in terms of like drug regulation, the FDA, clinical trials are what's done, prospective clinical trials, but there has been, I don't know, over the last 10 or 15 years, there's a lot more about post-marketing studies, real-world evidence, post-marketing safety. Those are using large observational data sets that are sort of, which would require the use of causal methods typically in this drug, that are complementing the evidence that comes from, you know, a more traditionally conducted randomized trial. I don't know this world super well, but
well, I could say a little bit about that. So there's the two key issues for me are confounding, which is what we're focusing on here, which affects internal validity. And there's effect modification, which is a very big issue that affects external validity. And randomized clinical trials are very good for dealing with confounding, less good for dealing with external validity, essentially because you don't have random selection of participants in a randomized trial. And also, you tend to have relatively small sample sizes, so you don't have very much power to look at effect modification. On the other hand, clinical databases are relatively weak on effect on confounding, unless you have really high quality databases where you are measuring confounding, and that have some potential for looking at effect modification simply because they're much larger, and also they might be more representative than a randomized trial, so they might be better for external validity. So I think the future for medical studies is sort of trying to combine the strengths of randomized trials with databases and other big data sources. Now, in the environmental area, you don't really have much randomized studies, so you have different types of observational studies that might have different strengths in terms of sample size and in terms of how well they're dealing with confounding. But the issue of external validity, which hasn't been discussed very much here, I think is quite important in the environmental area. And I would mention the paper by Tiding and Lewis. They have a very good discussion paper on this that's a debate. So some epidemiologists don't think you have to have a randomized out of selection of units in an epidemiology study, whereas statisticians, I think, are more in favor, more tuned in to the benefits of randomization in terms of where you select units. So there's a very interesting discussion of that. Tiding actually died last year with Shane, one of the statisticians. Rambling on a bit, but anyway.
Very good information.
Some of the benefits of partiality in the confounding.
Could you give him a mic so they can't hear
Where in areas that may have either one footprint of the whole hard hang, for example, like India, China, or increasingly now in Europe. But there is some of those models being used and having time to look at.
yes, yes, they are. I mean, for coal specifically, yes. And somebody, apparently Sarah mentioned the study in China that was implicitly about coal, not power plant, that used methodologies that are really used. So they are picking up internationally. I think that was the question. I didn't catch the first.
I guess the other part would be how far, however, range of the model that we have to I guess we were thinking like along East Coast, for example, the model we tend to be larger ranges, international.
Yes. Yes.
I think following up on that, how would something like wildfire smoke, which really mask the signature, impact your type of model? Because we know that there's fires where so theoretically can prove that, right? And
Yeah.
with the weather.
So I think You can't. This is, and people do it, right? So whatever I said about a coal power plant, there are people doing something analogous with for wildfires in the Western US. But this is where I think the distinction of whether you're talking about sort of receptor-based perspective or a source-based perspective is important, because what we did, at least in this example that I took, was we started with the coal power plant. So we knew what we were getting out of that was not wildfires, or wildfires. That it's not wildfires because we specifically modeled it from the emissions to the location. So that was the source. And so there's no aliasing with emissions from other sources. In a receptor-based thing where we said we're going to look at the pollution in a location, now we have this problem and we've got to decide, well, where did this pollution come from? Which a lot of EPI works this way, in which case you do have this aliasing between, well, is this PM from a wildfire, or is it from traffic, or is it from a power plant?
Right, but the problem on air pollution is that even if you're only tracking coal emissions, like the outcome that you're following is still so confounded by everything.
I see what you're saying, yeah. No, you're right. So like, I guess in a perfect world, you would have some measure of exposure to all of these different sources so that you would either view it as a multivariate thing, or you would adjust the analysis of coal for the presence of wildfires. With coal, what's kind of lucky about it is, first of all, well, the studies we did were back when coal was a lot more prominent in the US, so that was before these big wildfires. And also, there are not many coal power plants in the Western US, where the biggest wildfires are. So there's a little bit of convenience thing in there, but I mean, you're exactly right. And this came up all the time in the PM ISA. So like, how are we going to do this with these big wildfires that are, sending PM all the way across?
We had longitudinal data, so you had before, after. In some senses, these wildfires might be an opportunity for statisticians. And unfortunate. And somebody should write a paper about the effect of wildfires on wildflowers. That would be
Yeah, right. We're going to draw a flower for you. Yeah, I mean, I'll just chime in, exactly as Cory was saying. I think the field started out very much with this receptor sort of, construct and saying, oh, what comes from it? But actually, there's this amazing data source that was produced by Aaron McDuffie and Mike Brower up at UBC, where they have run sort of like what you've done for the coal-fired power plants, but they ran these deterministic, dispersion models where they selectively excluded one source at a time, and then they predict what happens to pollution. What's cool about that is it's not just these primary, emissions that you might think about, but actually sort of what happens on the whole ecosystem when you remove emissions at a time. And actually, we've incorporated that into a longitudinal study in the United States. And my student just circulated her first paper on it yesterday. Stay tuned, because we are exactly trying to do that, where we're saying, like, what's the impact of coal adjusted for, emissions from all the other things, wildfires, all those pieces. That can be pretty interesting. We're going there.
Great discussions. So I think we already touched some of this, but just wondering, like, over the years and from your perspective view, like, how do you think about, is there any other statistical method or challenges within causal inference that you think will be very important for air pollution epidemiology? So we'll go first with Tim, and then Rob and Sarah.
Yeah, sure. I can comment on that. And again, not so much specific to causal inference, but just air pollution epidemiology in general. And then continuing my theme of critiquing measurements as being a data generator, more so of a data user. The cool work that Cory and others are doing with regards to weather and meteorological variables and confounders, and also related to causation on their own. Going back to just how these exposure measurements, these air pollution measurements are created in the first place, they are impacted. The quality of the measurements themselves are impacted by local meteorology. Things like how much water vapor is in the air, relative humidity, what's the temperature. Cory talked about those secondary particles that are formed. Some of them are semi-volatile. So they exist as a gas on a warm day, and they exist as a solid, as a particle on a cold day. And many of these monitoring devices are very susceptible to the effects of water vapor, to the effects of temperature. And so that there are some, probably beyond uncertainty, some inherent biases right off the bat with just the exposure data itself. It continues to be a challenge for air pollution epidemiological analyses.
Yeah, so I'm interested in measurement error issues, and actually I'm currently doing some work with Qishuan Chen at Columbia, a student of mine, on dealing with multiple exposures that have measurement error using missing data type methods, actually trying to multiply impute the missing values with the calibration sample when you have calibration, an external calibration sample. So I think there are some potential for better methods for handling multiple measurement error on multiple variables. The limited detection stuff is something that I find quite interesting. The typical way in which limited detection is dealt with is wrong, in my point of view. The classical calibration approach is just wrong from a Bayesian perspective, and you can do better than that. And it's always interesting to me that you throw out the data at the bottom of the scale because it's below limited detection. But often the values that are above the limits of detection have more measurement error than the ones below the limits of detection, because the measurement error tends to increase with the values. So that there are some interesting things there with non-constant variance. The other thing I would say is that I think it's very hard to do this dose extrapolation. I was actually working in the Office of Radiation when I was working with Rosenbaum and Rubin, and you're trying to extrapolate into the high tail. Often, so you're looking at where the data is generally very sparse. And it seems to me that the EPA tends to design studies based on assuming a log normal distribution, which is making an extremely strong assumption since you have no idea what the distribution is out in the tail anyway. So I think that's a challenge. I don't quite know how to deal with it, but there are strong dependence on assumptions there.
Certainly. I think the first two issues you mentioned about measurement error and the measurement limits actually is related to what Tim has been doing. That actually reminds me, in the literature for measurement error, sometimes the measurement error is additive to the model versus the other kind of classification measurement error. So, the later actually is harder to handle.
So this is non-differential measurement error assumption, which plays a role that is valid for some kinds of studies, but not for others. Relaxing that assumption would be difficult.
Definitely. For the other one you mentioned about the normality assumption, I have seen some papers talking about the distribution of the pollutant is bimodal, and actually the Bayesian method, they use Bayesian method, they could handle that.
Yeah. Well, I'm a Bayesian, so of course I'm going to do
everything can be done.
So I mean, the implementation stuff that we're doing is basically using Bayesian models.
Sarah, any thoughts?
Yeah, I think measurement error is obviously something really important, and it's complicated in the environmental world, and it can have sort of interesting and unexpected implications on the or beta coefficients. Non-linearities that we experience in our dose response or concentration response curves, I think, make it more complicated, as well as this mixture issue. So I think those are pretty interesting, important, and people are working on them. The other thing that I'm really obsessed with right now is confounding by place and time, right? So our variation that we use in trying to understand the impact on health either come from time, so like day-to-day variation, or space. So comparing somebody in St. Louis to Ann Arbor or something. But there's a lot of other things that can vary over time and place, right? So we see these time trends you saw of air pollution levels dropping. The Clean Air Act has been largely successful. And health has also been improving over time, but there's other reasons why those things happen. And so for me, I think it's a fascinating question that I've been struggling with, and welcome all the biostatisticians to join me in trying to figure it out, is how much of that information do you say you're just going to throw away because you're worried it's confounded, right? Either between meteorology or something else. And how much are you willing to use? And how do you know? So from my personal perspective, I think that that's something that would be really interesting to see more research. And I'm working with some biostatisticians on it, but
Maybe some time verification models.
So we're trying to combine data sources. I mean, I talked about combining randomized trials with observational studies in the medical setting, but I mean, if you had a variety of environmental studies, some of which had good control confounders and others that didn't, then in principle, I mean, you could use missing data methods to combine the information across those sources. But I get into trouble because I say everything's a missing data problem.
Yeah, that's true.
well,
They can-
Well, no, actually, I had a trouble. I got into a debate with Judea Pearl at one time because Judea thinks everything's a causal inference problem. So he was giving me a hard time because I said everything's a missing data problem. Sorry.
oh, I just was gonna say, I'll never forget being in a class one time when we were talking about unmeasured confounding, and the professor reminded us, that we don't know everything. So it's hard to know what you don't know, which is why I really like dates, because I even in data sets, I have incredibly rich information. I mean, I've got, economic information, I've got health information, I've got all kinds of things. I still worry that on a national study, that I can't just consider everybody everywhere equal, even though I have their covariates. So, there's regional differences and everything else that in health access and all these other things and behaviors that I think are hard to capture.
You could get into the National Children's Study and why that fell apart. That's another discussion.
In terms of the statistics literature, for those of us who are oriented towards the statistical literature primarily, I'd say following on these things that have been mentioned there, is sort of a budding literature on spatial causal inference, which is something that it's like two very different kind of communities of statistics, which are spatial statisticians and the more problem people. There's a little bit of an overlap there, and there's some cool work coming out there, which is meant to do, I think, essentially address the challenges Sarah raised. And then the other thing with, I'll just sort of, I don't know if I'm plugging myself or what, but the potential outcomes causal inference formulation of this type of multivariate exposure, multiple environmental mixture exposure question is popping up a little bit in the statistics literature. What kind of estimates even make sense in this type of setting? When we all kind of know that it's the mixture of contaminants that we're interested in, and this kind of one contaminant at a time approach testing. And so the professor at University of Florida and Joey Antonelli, I'm working on a little bit with that, and there's some other things popping up in sort of epi methods and statistics literature there, which are exciting.
I'm curious, because Sarah, you were mentioning like what data do you keep versus what don't you keep, but I think the question that we used that you also were talking about at the beginning is what studies do you keep as we continue to develop these new, better methods, and we, things that are developed today will be old news in, 2 weeks probably. The way everything's getting faster and better and bigger and more detailed. So when do we start actually throwing out data sets, throwing out studies and saying like, this is not enough anymore? And when do we stop like trying to find the next best method and say like, we got it, this is good, 95%.
I'll say my perspective that I actually think the second problem is the bigger question, right? So I think flawed studies, you could tell that they were flawed even when they were the best that we had. We would say, and that was why the causality evidence would be like suggested but inconclusive because the data set wasn't good enough. We knew it at the time, it was just that we didn't necessarily have better work. So as the new and better work comes in, I think that's when it comes to causality. The second question is very interesting to me and something that I become passionate about because we have limited resources as a society, right? And as much as I like air pollution research, and that's been my career, even I am like, I'm not sure that it's valuable to spend more money on some of the simplistic questions that we already know the answer to. So I think as scientists and as a community, we have to be understanding that when we take money to ask the research questions that we're taking money away from others. And so the issue of do we have enough evidence to decide it's possible right? At that point, maybe we need to either make sure we're answering the questions of like, okay, we know that particles are causal for mortality. Which sources should we regulate? What's the impact of this intervention? But do I need yet one more study that says it causes death? I personally believe no. And you know, as Cory was saying for his research, like I haven't given, this is my area of expertise, but I think it's an important thing that as scientists we need to ask ourselves, are we really adding to literature? Or do we already know this answer?
Fair point. Any
If
other?
it's possible to get access to different studies, then there's a lot of statistical interest in combining information across studies. So that seems potentially promising. If you had one very high quality study that had very good measurement confounders, for example, you could use that information for other studies where those confounders might be missing, but maybe it's a national sample, National Health Interview Survey or something. So there's different sources that have different strengths. You can somehow, if you have access to those data and you can combine information across data sources, you could do better than you just looking at one study at a time, which is typically what we do.
All right, so other questions? Yeah. Go ahead.
Yeah, so I don't come from a research side, or definitely not a stat side of things. I come from more policy side and like, so I'm really curious and interested in how this works on estimating cumulative effects of pollution in communities versus looking at how, because when we talk about like citing new projects that might like increase air pollution, we usually like the EPA and like the state department will look at how that one thing is going to impact, not how that impacts what all the other impacts are going to impact that. And so I'm just curious around the like accessibility of your research, and then also like for community groups, but also how you see this role in the shift from individual impacts of projects to like the cumulative impact. Hope that makes sense.
If it does make sense, I don't know if it does. I mean, so there are various other sort of indices out there now that are, I think, more about kind of like cumulative, if not exposure, like at least cumulative vulnerability. Greg, you would probably know more about that. And I think that kind of is how they're being used, is to get some more holistic notion of sort of community vulnerability when a new project is being cited. So I certainly can't say that any of my work contributes much to those types of questions, but I am close enough to that type of game to see that there's a lot of movement in that direction. Unfortunately, the Clean Air Act is set up to regulate pollution one at a time, which is a little bit crazy scientifically, but then, you know, it's the framework we have. It's sort of the framework EPA has to work with right now. Anyway, I'm not sure that really answers your very good question.
There is a question on Zoom. It's asking, are you considering cumulative burden of pollution exposure? Yeah, it's kind of similar. So in these methods.
I mean, there's sort of two notions of cumulative, at least in one, that come to mind. Cumulative in the sense that you said, like there's lots of other exposures out there. So are we missing is it a forest for trees situation when we just focus on one thing?
Yeah.
And then there's sort of cumulative exposure in terms of long-term, like over time, which is sort of why EPA separates these determinations between long-term and short-term exposure. The long-term one is supposed to be like a marker for like lifetime. So, that's not really what you asked, but it is also another notion.
We'll take the last question. Yeah, go ahead.
Yeah, I think I was kind of going back to your question or your comment about the challenges of, you know, when you sort of move on from a certain body of research, or sort of types of research questions, depending on, you know, the needs of our field, the needs of society, and sort of in the beginning of your talk, you posed different questions that we could ask. Like one is, what are the effects of X? You know, it's going on at outcome, and then what are the, you know, effective intervention, right, on that. And so I'm wondering, you know, do we just need more of the latter, right? And sort of what, like you mentioned, your student work now,
Yeah.
but sort of, is there more of a system where there's how can we make that happen? Is that really, or is that?
Yeah, I mean, I guess I can say, reading the pulse of the environmental epidemiologists who do this kind of research, there's definitely more and more movement towards, interventions and trying to understand those impacts or susceptibilities, or key sources or mixtures, like, that is where the field is going. I can tell you, for example, another one of my students who probably one of the cooler papers I've worked on in my career. If I end tomorrow, I'll be super happy. But we're looking at the impact of funding that the EPA gave to replace old stinky school buses. So they did a random lottery to decide who got the money and who didn't.
Must be a problem.
I don't see any questions. No, well, I don't know, but so I mean, I think those interests of saying, what's the impact on absenteeism among kids who won the lottery money versus those who didn't? What's the impact on their student educational performance and health? So I think that the field is in general trying to ask more and more of those questions rather than just I mean, my joke is always like, we don't need a study that looks at air pollution earlobe lead. Fascinating. No one's ever looked at it. Novel, super new, but not important, right? Like we already know it kills you, so we don't really need to know about earlobe. I think
I mean, that's how I got this. A little bit of that shit Sarah describing is how I got into this. I was a postdoc in 2010, and I didn't know anything about environmental health. I thought I was bad. I studied causal inference methods. And I joined an environmental health research group. And there, at that time, again, it was around 2010, the word at the time was accountability research, which was all about the effects of interventions, regulatory interventions in particular, but not exclusively. And to me, as someone who had a causal inference background that was something new to air pollution, I was like, all these places are calling for estimating the effect of interventions. Why are people still estimating the effects of pollution to answer these questions about effective interventions? Like, why aren't they listening? Was sort of how I felt. But it was just that, different fields have their own cultures and preferences. So that was sort of the early stages of this shift to try and, move the frame a little bit to these questions about particular interventions. And I think it's sort of mostly continued in the way that we described it. So it can focus on effective interventions as well as natural experiments, which is sort of similar, and focusing on sources, particularly.
The example I use is gun violence. Actually, what's the causal effect of the intervention on gun violence? That's the issue, not what's the cause of gun violence. Yeah. We all know there are lots of causes of gun violence. Whichever side of the spectrum are, you can argue for one or the other. But that's not getting into.
The other way in which the field has moved, I think, in an important way is the development of the Global Burden of Disease Project, which is published a lot in the Lancet, but actually, there's two groups, there's the WHO and there's the IHME in Seattle. But that framework has come really strong into the air pollution world. So now it's very common that people will extrapolate the results. So they do these, sort of more traditional methods of saying, oh, each unit of air pollution causes this many more deaths. But then what they'll do is they'll take the exposure distribution of the entire population of the United States, figure out what would happen if they change it, and then predict for you in those scientific papers, which gets a little bit of what you're saying, but not quite, numbers that the policymakers can use. So actually in our first study, I came out, a different one from Seattle, I came out and in that paper, I say, 1.4 million absenteeisms a year could be saved by switching to clean diesel, because what we did is we extrapolated our results, and Kamala Harris' office called me, right? Regularly I get these things, and actually it became part of the infrastructure bill. The funding of clean buses went into that in part because we were able to show, these impactful numbers that help to change policy, which I think is maybe even more at your question.
All right, so thank you all so much for this discussions. I found that although one of my hardest job is to cut this Excellent. I'm for break. So let's give a big applause to our speakers.
Hi everyone, I am Yanlin Tong, a second year master student from Department of Biostatistics. Nice to meet you all. And today my topic is spatial visualization tool and spatial modeling on Michigan urban environmental health data. And this is a joint work with Professor Wang. Thank you so much. So first, as for our big picture, whole picture of our whole background of the project is called the Urban Hearts. Urban Heart stands for Urban Health Equity Assessment and Response Tool, launched by the WHO in 2010. And based on the public Michigan urban health data, our project is to develop an urban hearts to measure and monitor the urban health issues. And our outcome or result could be the basis of further research or provide some recommendation for the policymakers. And the following are our data sources. And as for our data structure, first we have 874 census tracts from 24 municipalities. And I think this Google map can give you a very straightforward view. You can see from this map, our census tract we focus includes like some census tract in Grand Rapids, some census tract in Lansing, Ann Arbor, Dearborn, Detroit, Flint, and so on. And our data also includes 77 variables, including some demographic variables and other variables from other 6 domains, like health outcome domain, including percentage of cancer population, like health behaviors domain, such as the percentage of drinking people, or healthcare domain, income, employment domain, and so on. This is our data structure. And here is also some straightforward heat map visualization. I just like pick up 2 measurement or say indicators from our data. The first is the variable asthma prevalence. We can see this heat map. In this map, the darker the color is, it means the higher the percentage of asthma prevalence is. So we can see like from here, near some area near Dearborn or Detroit, the color or say the asthma prevalence is very high. But here is Ann Arbor, we're very good. And the next is the PM 2.5 concentration. Similar as before, the darker means the higher PM 2.5 concentration values is. So here is the scientific question we want to investigate here, is how health outcomes depend on the environmental measurements, which means we want to investigate the association between them. However, the main challenge in our project is how to account for the spatial autocorrelation while modeling. So what is spatial autocorrelation? It's just like the values of some variables from similar or neighboring area, maybe very similar with each other. So this is called like spatial autocorrelation. So actually we have many outcomes, but I only want to illustrate one outcome here, which is the asthma prevalence among adults. So in our model, the predictors are also shown in the table, which is PM 2.5, gender, age, unemployment, transportation cost information. So next, to build our model, the first thing we need to do is to test if we have spatial autocorrelation in our data or not. So first we use the LM test, which is a very useful test to test for the spatial autocorrelation. So after doing the LM test, we can see there are very significant spatial autocorrelation in our data. So this motivates us to do the spatial regression or say spatial model for our model. So here are 2 very useful spatial regression models. The first is called spatial error model. So from the picture, we can see this error model focuses on the spatial autocorrelation between the residuals from the linear regression. And the next model is called the spatial lag model. It focuses on the like it focuses on the dependent variable y in place I will be affected by the outcome variable in both place I and j. So specifically, the spatial error model accounts for the spatial dependency on the residuals, or say error term. And if we test the very significant spatial dependency in the linear regression, the spatial error model would be a very good choice. And the spatial lag model accounts for the spatial dependency on the outcome variable. So if the outcome at position I is both affected by the outcome at position j and the covariates, the spatial lag model will be a very good option for us. So we tried both of the two models. And finally, according to the AIC, we finally choose the spatial lag model. Because the spatial lag model's AIC is significantly smaller than the AIC from spatial error model. So the table is the output from spatial lag model. So we can see from the coefficient of PM2.5 concentration is 0.2, which means if we have 1 unit increasing in the PM2.5 concentration, the outcome, or say the percentage of asthma prevalence, will increase 0.2. But the model of above I introduced can only give like a global or general coefficient for each covariance. But this model, called the geographically weighted regression, GWR, can give every location a unique covariance coefficients. So you can see this is a model of GWR and the coefficient estimation. So from these two formula, we can see every location has one unique GWR model, and one location have one unique coefficient estimation bit I hat. So this is the output of the GWR model. Focus on the PM2.5 concentration, the mean value, the mean coefficient value is around -11, and the median is 2, and the max value of the coefficient is 50. And I want to take Grand Rapids City as an example. So you can see for the city Grand Rapids, the coefficient of PM2.5 is around 3.7, which means if there is 1 unit increasing in PM2.5 concentration, the percentage of asthma prevalence will increase around 3.7%. And the last picture shows on the right is the coefficient of PM2.5 in different locations. So we can see for different location, we have different coefficient estimation. And you can see like for this red area, maybe near Dearborn or Detroit, this coefficient is, the value is very larger. And for some other light area, this coefficient for PM2.5 is not very large, it's very small. So I think all the models I introduced above are related with the spatial regression model, and different models have different disadvantages and advantages. Okay, so I think that is all for today. Thank you so much.
Hi, everyone. My name is Margaret. I'm a PhD candidate in biostatistics, and I work with Peter Song. And today I'll be talking about critical window selection in scalar unfunction regression using mixed integer optimization. So first I'll do a brief introduction on functional data and functional data analysis. So when we have functional data, we're thinking about data where the covariate or outcome of interest is the curve itself. So we're looking at observations on subjects where you can imagine we have values of xi, where xi, ti, where ti is a continuous, so whether over a continuous domain of time or kind of anything else. And when we think about the basic characteristics of functional data, we consider them to be high dimensional, that they're structural or temporal in nature, and that they're recorded over this continuous domain. And then the functional data analysis is the methods that we've kind of a community developed for analyzing this functional data when we believe that these curves should be evaluated more holistically. So an example of some functional data that we may see in the environmental realm We could think of exposures over time as a function, such as PM10, PM2.5, or O3. So here we see, so in the middle one, we're looking at our curves, and we can kind of see that the curves take specific shapes over time. So we're considering more the structure of the curve itself as our covariate of interest. So for a scalar on function regression, this is what the basic model might look like. Just to break it down, we have a scalar outcome, so y, and we are regressing that on a functional covariate and trying to estimate the functional predictor. So, and here we have the green X is our functional predictor, which we could think of as one of those curves that I showed in the previous slide. And we're trying to estimate the functional beta parameter. People may have seen some things like this when you're trying to estimate maybe using spline regressions or things like that, a functional beta. But in this case here, what I'm trying to estimate, my functional beta, I want to estimate it as more of a step function. So I want to be able to select critical windows of importance on our outcome where we've fused together the interesting beta windows. So some methods that people may have used could be under the world of L1 regularization. And here I'll be introducing kind of a different realm of L0 regularization. And I'll introduce that in the coming slides. But my main objective is to investigate these functional curves and be able to develop a method that can handle really highly correlated data. So a lot of times the functional data are time data is pretty correlated with each other. I want to be able to develop a one-step process so I can estimate change point estimation and the parameter estimation in a single step rather than methods that might look for change points and then put that into a different model and try to estimate a parameter estimation. And I want this to be computationally efficient. So there could be different ways that it's theoretically possible to solve these issues, but computationally it takes far too long to be feasible. So as an introduction to this L0 regularization space, it's best to introduce it using this best subset problem. So people might be aware of this when you have a very high dimensional set of covariates X, and you want to be able to select which ones are actually important. So you may have 100 different variables, but you know they're not all important, and you want to be able to select, say, 10 or 20 of them and really understand what's impacting your outcome. So solutions that we currently have is could be lasso, where you are minimizing your objective function, which is kind of the top line of all the math symbols there, subject to a penalty function or a penalty, which we call the L1 penalty. And in this penalty, you're minimizing the absolute value of your beta coefficients. So people who use lasso or fuse lasso or things like this in their methods, kind of in the L1 norm space. Some issues with this approach is that it can induce biases in estimates and that there are limitations and instances of high correlation. There are ways to work around this, but for now, we'll be introducing what is the L0 norm space. So here we are still minimizing our same objective function, but now our penalty, we're not using an L1 norm, we have our L0 norm, where we're limiting the number of non-zero coefficients rather than shrinking our coefficients, the absolute value of the coefficients, minimizing that. So the big difference is what I've circled here in green, where we are limiting the number of non-zero coefficients. So in this space, it used to be considered computationally infeasible to do this in the L0 space, just based on limitations of computers and technology, algorithms. But a computational feasible solution to this best subset problem was introduced by Bertesmith using mixed integer optimization, which looks at the minimizing the objective functions that we looked at and then using a set of linear constraints to solve the issue. What we want to do now with this solution is provide the extension to functional data and be able to perform the fusion in order to get what we saw as a step function as our functional beta parameter.
So to kind of further explain how it works, I'll bring my example that I've been working on in my research. A caveat, it's not quite environment related directly, but as shown in the other functional curve, that could be used for different environment questions and like that. So my outcome of interest is biological or epigenetic age. And what this looks at is kind of the difference between how you chronologically age throughout time and how your body ages. So as we look at this picture, we see the people who are along the actual line, like they're feeling young when they're young and a little bit older as they get a little bit older. But then as we have people who are, we call biologically younger when they maybe are healthier than we would expect of someone of their age, and vice versa if they're older. So our functional predictor we're looking at is physical activity. Here I am summarizing physical activity in a slightly different way than we normally see. Many times people will take continuous physical activity data like we see on the left and summarize how many minutes people have in certain levels of activity, such as sedentary, moderate, or vigorous. Instead here, I am creating a summary curve called the occupation time curve, which looks at the percentage of time people spend at different levels of activity. So we can see that 100% of people's time they spend doing at least nothing. And the percentage of time that they spend at different levels of activity decreases as that level of activity increases. So what we end up with is continuous curves for each person, summarizing the physical activity over a certain period of time. And what we can notice when we start to compare curves of different people is that the shapes of the curve take distinct shapes depending on if they're considered less or more active. So as we can see from the top two curves with the less active person, their curves decay quickly and start to flatten out very early, whereas more active people have a more distinct shape as they are more active in the later activity times. So we're going to use those curves in order to use those curves as our functional predictor in order to estimate these functional beta estimates in terms of these step function. So we can get what critical windows of activity impact our outcome. So how we do this is we consider on the far left, we have an occupation time curve. And the way we are getting like a high dimensional set of variables is that we are looking then, instead of the full integral of the curve, we're chopping it up into many small intervals and thinking of the area in each of those sections as its own covariate of interest. And then what we want to be able to do is use our L0 fusion approach in order to look at which of these many dimensional X variables have a similar effect on our outcome. So to show some simulation results, so just to prove that it works, I'll go through this quickly. We're able to very accurately estimate at least a three-group model in this example. So when we kind of estimate critical windows of size 40 each, so 40, 80, and then up to our max of 300, we're able to very accurately estimate the cut point or the change point and the parameter estimation. And we're able to do this as our sample size decreases from 500 all the way down to 100. For the quick application, we have the occupation time curves for a selection of about 500 subjects from the ELEMENT data set, which is a research cohort study that Michigan here participates in. And for the results here, on the top line, I have what our model is. So our functional data is this occupation time curve, and we want to estimate our beta parameter with its effect on epigenetic age. So this model found a two-group model where the very extra sedentary time was a positive association with their epigenetic age. So how we would interpret this is that more time and this less active activity window was associated with a younger epigenetic age. So overall, this looked at kind of adapting this L0 regularization to a fusion adapted model using this mixed integer optimization where we looked at a family of linear constraints. And it was a one-step process to estimate both the change point and the parameter estimate. And while I looked at functional physical activity and biological outcome, it could be easily applied to other types of functional data.
Thank you.
Hi, everyone. My name is Sam Fansler, and I'm a second-year master's student in biostatistics, and I'll be presenting on cardiovascular disease mortality prediction using metal mixtures and NHANES. So quick motivation for this project. Cardiovascular disease is the #1 cause of death in the United States. So it's crucial to identify exposures that predict cardiovascular disease to learn how to protect against this leading cause of mortality. And the Framingham Heart Study is a long-term study that began in 1948 in Framingham, Massachusetts, and it was designed to discover predictors of cardiovascular disease. And so the study has been going on for over 60 years, and it has uncovered numerous risk factors of cardiovascular disease, which has culminated into the Framingham Risk Score created in 1998. And that risk score used age, sex, smoking status, diabetes, systolic blood pressure, total cholesterol, and HDL cholesterol, among others, as predictors. And these predictors are still considered the prominent predictors for CVD today. And then more recently, the atherosclerotic cardiovascular disease study in 2019 compared 3 previous risk scores, including the Framingham risk score. And they found that race is an additional factor for CVD risk that hadn't been looked at in previous studies. And even after these 2 studies, there's still a gap in the literature. Firstly, environmental risk factors for CVD mortality haven't really been looked at. And secondly, there are a few studies that implement machine learning methods to try to improve prediction performance. So these gaps motivated 2 main research questions. Firstly, we wanted to see if adding metal mixtures to our model improved CVD prediction performance. And secondly, we wanted to see if we can further improve performance using these statistical machine learning methods. So for this project, we use the NHANES dataset, which is a cross-sectional survey that spans over 60 years of 2-year cycles. NHANES combines laboratory data, survey data, and health examination data to provide a comprehensive nutrition and health database that is designed to be representative of the US population. And so for this study, we used the cycle from 1999 to 2016 to maximize the number of available environmental metals while still obtaining an official sufficient sample size. And CVD mortality data was linked to NHANES through the National Center for Health Statistics National Death Index with follow-up through 2019. And both of these data sets are publicly available on the CDC website. So we then split the data into 50-50 training and testing data sets to train the prediction models and then use the testing data set as external validation for prediction performance. For our exposures, we began with the existing predictors for cardiovascular disease from previous studies, including age, race, sex, smoking status, systolic blood pressure, total cholesterol, HDL cholesterol, BMI, hypertension, and diabetes. And then we added the available metals from the NHANES cycle we chose, which included 14 urinary metals and 3 blood metals, and both log transformed to account for the natural skewness in the data. And then for our urinary metals, we additionally adjusted for urinary creatinine to account for hydration in the participants. And then our outcome measure was cardiovascular disease mortality, as described before. So here's the descriptive statistics table for our mortality data and traditional predictors. So our sample size was roughly 7,000, split 50-50 into the training and testing data sets. A few things to note here is the age of our participants is on the older side because those are the participants that are more at risk for cardiovascular disease. And then there's also a roughly even split between the training and testing data. And then one specific thing to note is the very low proportion of CVD mortality cases in this data set, so at about 6%. So this survival curve for the CVD mortality kind of represents that low proportion from the descriptive table in the previous slide. So you can note here that the survival probability never really dips below 95% after 16 years of follow-up, which could have some impact on prediction. So we started with the classical model for time to event data, which is the Cox proportional hazards model, which models the probability of an event, which here is CVD mortality at time t, based on the baseline hazard for all participants times an exponentiated linear combination of predictors. So the main criterion we used for prediction performance was Carroll's Concordance Index, or C-index, which measures the concordance between predicted survival times and observed survival times. And it's a value between 0 and 1 as it represents the proportion of concordant pairs in the data set. And just to give an idea of what a good C-index would be, a C-index of 0.5 is pretty much equivalent to a random guess. So anything below that is not an improvement on a random guess, and above that is an improvement. So in addition to the Cox model, we wanted to explore whether machine learning methods could further improve prediction performance. So the machine learning methods we used were the ElasticNet, regularized regression, and survival random forest. ElasticNet is a regression method that imposes a penalty term on the beta coefficients to introduce shrinkage to each predictor. And ElasticNet uses a combination of the L1 penalty from lasso and the L2 penalty from ridge regression in order to perform variable selection while handling highly correlated predictors. So the so-called unimportant predictors shrink to 0, which performs variable selection, which is ideal for our complicated metal mixtures model. We used tenfold cross-validation to select the optimal penalty term that produced the highest C-index. Survival random forest is a random forest method for right-censored time-to-event data. It's an ensemble method that combines many decision trees to prevent overfitting. And this method has multiple hyperparameters that were tuned for optimal performance, such as number of trees. And it is a non-parametric method, so non-linear terms such as interactions are accounted for automatically in this model. So for each of our models, we began with a baseline using the traditional predictors from the existing Framingham and ASCVD risk scores. We then trained a model using the main effects of the metal variables, followed by a model including the main effects plus the quadratic and interaction terms for the metals to account for nonlinear effects. And you can note that for the random forest, there's no differentiation between the main effects model and the interaction model, since the random forest accounts for nonlinearity. Prediction and calculation of C-index was done using the testing data. And so our main result is that the highest C-index was that of the cost proportional hazard model with only traditional predictors from previous studies. So adding metal mixtures to the model did not improve the prediction performance for the Cox model. And in addition, these machine learning methods also did not improve prediction performance. One thing to note in particular for the ElasticNet is that adding these metals did slightly improve the C-index from the traditional predictors. That is likely due to the variable selection that it performed. It reduced the noise by only selecting the important predictors, the ones that explain the most in terms of CVD mortality. So from our findings, our main conclusion is that the existing prediction methods and predictors are optimal when predicting CVD mortality. We found that adding metal mixtures to the model did not improve prediction performance, and neither did machine learning methods. One possible reason for these findings is the very low proportion of CVD mortality cases in our data set. This low number of events could have made prediction difficult for the more complicated models, such as the metal mixture models and the machine learning methods. In addition, the dimensionality of the data was rather low, which is an optimal condition for classical prediction methods such as the Cox model. And then finally, the metals, the ElasticNet does handle highly correlated predictors, but the metals were actually not as highly correlated as we believed. So that's another reason why the Cox model may have outperformed those machine learning methods. One strength of our study was that it was a longitudinal study with 16 years of follow-up. In addition, the previous studies had most, if not all, white participants, and the NHANES data set provided a much more diverse sample. And then finally, our study included advanced statistical methods that could be applied to other prediction studies. Our study did have some limitations, including the low proportion of CVD mortality cases as mentioned earlier. In addition, the C-index was already quite high for the traditional model, so there was not a whole lot of room for improvement there. Future directions for research include investigating the interaction between urinary metals and creatinine. We found that in the ElasticNet, most of those interaction terms that were selected were between urinary metals and urinary creatinine. And we found that increased the C-index. So investigating those interactions may prove fruitful when investigating prediction in CVD mortality. And then secondly, we did find that urinary metals do not really predict CVD mortality that well, but there are a lot of other environmental chemical families, such as pesticides, that could have a possible effect on prediction performance for CVD. So I'd like to thank our funding source, the National Institute of Health, as well as my collaborators and mentors, Soumik Park, Carolbeth Korn Prize, and Wang. Thank you very much.
All right, hello, my name is Soumik. I'm a fourth-year PhD student in the Department of Biostatistics. Welcome to my talk. This is primarily based out of the work that I've been doing for my first thesis chapter by Dr. Song. So as you can see, there are some keywords in this title. We posit a new framework of causal discovery, which sort of treats asymmetry in bivariate data as a signpost of underlying causality. And in order to shine a light on this signpost, we'll be using some well-known information theoretic coefficients, which I shall explain in the next couple of slides. So here are the deliverables. I'll start by introducing the topic. I'll talk about the framework that we're positing. We talk about the deliverables of that framework, and also we have an epigenetic example to look at. This is also another element data set. The discovery of causal relationships in bivariate data in observational studies is a fundamental problem in science. So a typical question might be whether change in altitude causes change in temperature, or whether change in temperature causes change in altitude. So when you have some domain level knowledge, this is not a question, this is something you use in your research. But when you don't have domain level knowledge, you might want something like either a causal discovery tool or something with which you can help confirm a hypothesis that you might have. So even on simplifying assumptions like no confounding, no selection bias, and no loops, this is a very hard problem to tackle. The gold standard would be controlled experimentation, but that's often unethical or it might be too expensive, in which case we need to be able to talk about examining statistical patterns within the data to sort of shine a light on underlying causality. Our method is based on understanding or noting that asymmetry in a causal relationship may arise when one variable plays a leading role, in the sense that one variable contains more information in a bivariate framework and can be used as a more effective predictor as compared to another variable. So really what we do is we view asymmetry as a low-dimensional representation of high-dimensional causality, with the understanding that information flows from the leading variable to the variable which is being dominated. We propose a causal discovery instrument to study this sort of asymmetry using some well-known information theoretic terms like mutual information and conditional entropy. So on your screens here, you will see this term called joint entropy in a bivariate system, which measures total information in a bivariate framework. The total information in a bivariate framework can be decomposed. So you can think about the decomposition on the right side of your screens as sort of like an ANOVA-like decomposition, where you break it into a between groups and within groups sum of squares kind of thing. So here what we're doing is we're decomposing the entire information in the system, which we quantify using entropy, into three components. One component is called mutual information, which is a good measure of association between two random variables. So the moment-based analog for mutual information would be something like Pearson's correlation. The advantage that mutual information enjoys is that testing for equality to zero for mutual information is an if and only test for testing independence. That's not something that you can say for correlation coefficients all the time. In fact, most standard measures of association are symmetric. So you can't really tell which is the more important variable. And also the most standard measures of association are not good when it comes to nonlinear or more complex association patterns. So yeah, mutual information measures association, and conditional entropy measures the amount of information that we need to predict one variable X given another variable Y. So the total information in the system can be decomposed as a measure of association and a measure of asymmetry between the two marginals in the data set. So what we're really trying to say is we're trying to compare the amount of information you need given one variable to predict another. And we're saying that the more information that we need, that's a harder prediction problem, right? So we want to choose the variable which makes our prediction easier. And that's sort of like the underlying crux in terms of how we're approaching this causal discovery problem. So what we do is that we use these conditional entropy terms and we create this new statistic called the entropy ratio, which when equal to half is corresponding to a balanced situation where there is no well-defined asymmetry in the data set. If the entropy ratio of X given Y is greater than half, that means X is the dominating variable. If the entropy ratio of Y given X is greater than half, that means Y is the dominating variable. So really what we're going to do is we're going to use this symmetric mutual information and this asymmetric entropy ratio, and we're going to club them together to create an asymmetric coefficient, which can highlight underlying asymmetry in our data set. So as I mentioned, we're looking at this metric called the asymmetric mutual information. It's sort of like a scaled function of the mutual information. The scaling function or the scaling factor is the entropy ratio, which we've already mentioned is used to detect asymmetry in a bivariate data set. So we really try to propose this two-pronged approach to testing for association as well as causality. Step one would be to test for association, because if there is no association, it doesn't make sense to talk about causality. So assuming that we are talking in a framework where we have detected a significant association between the two margins of our bivariate data set, we want to move into a territory where we are in a position to talk about an asymmetry, which we treat as a weak or low dimensional representation of high dimension or potentially even infinite dimensional causality. All right, so here are the deliverables for our asymmetric mutual information framework. So we return a test for independence that gives you a p-value. If that's more than 0.05, that's where you stop. You don't need to talk about the presentation anymore. But if you get a p-value of less than 0.05, that's when you start talking about asymmetry and causality in the data set. So what we do is, I want to cut short my presentation because we're running short on time. So whenever we talk about asymmetry in an association framework, look at the delta statistic and look at the 95% confidence interval rather than the actual value. Look at the confidence interval. If it's on the right-hand side, if it's on the right side of 0, that means that X is the nominating variable and Y is the dominated variable. If it's on the other side, the converse holds. All right, so now I will highlight the element data set. So I will be focusing on a cohort of teenagers aged, not teenagers, the children aged between 10 and 18. A question of interest that researchers often have is a directionality between DNA methylation alterations and cardiometabolic outcomes. Now, the link to environmental science here would be that cardiometabolic outcomes are indeed impacted upon by environmental factors. So really, if we can find a sort of directionality between blood pressure, which is a cardiometabolic outcome we look upon, and if we see that that's in turn influencing DNA-based methylation, then that's a significant finding that we should be able to explore more. So we will be doing something like a target gene analysis. We have this target gene ATP2B1, the one's missing. We know that this target gene is already significantly associated with both systolic and diastolic blood pressure. More than 20 independent studies with sample sizes of at least 20,000 each report this association from the NEGRI GWAS catalog, and I'm just picking one from there. This gene ATP2B1 has 21 methylation sites, which are weakly correlated. So the important question we'll be asking, or we'll be trying to confirm with our method, is whether the association that ATP2B1 reports with both systolic as well as diastolic blood pressure are indeed reflected by our study. And if that is so, whether any of these individual methylation sites are significantly associated with this gene, with systolic or diastolic blood pressure. And if they are indeed associated, we're talking about some sort of asymmetry that arises. So I hope, sorry about the font size. So what I've done is, this is sort of like an inverted Manhattan plot. So on the y-axis, you see your CPG sites, which are linked to ATP2B1. The panel on the top on your left are minus log 10 p-values of the test of independence. What we're really doing is we're testing for association of systolic blood pressure on the left, systolic blood pressure on the right, and diastolic blood pressure on the left with each of these individual CPG sites, and I'm reporting a negative of log 10 p-value, sort of like a Manhattan plot. And what we'll be doing is, we know that these CPG sites are associated with one another. So we'll be doing something like a Cauchy combination test or a summary. You could use something else as well to check whether the finding you have is statistically significant after you've accounted for multiple testing problems. So we see that we do have some success with our method. The ATP2B1 gene for the element cohort with a sample size of 525 reports a significant association with diastolic blood pressure. There's just one CPG site which is driving this function. It's 17564245. That's interesting. And based on that, the one that you see with a minus log 10 p-value, which is crossing the Bonferroni threshold, what we'll be doing is we will be considering some sort of asymmetric test between this CPG site and diastolic blood pressure. And we do see that diastolic blood pressure seems to exert some sort of influence on the CPG side. Now, most of these methylation studies are still in their infancy, so this is a new result. The hope is that this will lead to more research in this problem. That's all. Thank you for your time.
Hi everyone, my name is Zhongzhe. This is a joint work with Professor Wang. And the multi-source data becomes common in scientific research. So one of the features that makes this multi-source data different from traditional integrated data is that each source will share a common set of subjects. So in the traditional data integration, so the number of sample size is increasing. While in this multi-source data, typically the number of sample size and the covariance are increasing simultaneously. So compared with a single data set, this multi-source data can incorporate more information and increase efficiency. And it is more representative when sampling is non-random. However, when this in the multiple source data, blockwise missing is likely to exist. So here is an example of blockwise missing data. Suppose the data are sorted by the missing pattern. So we have 3 missing patterns and 3 data sources. Source 1 may contain the variables that are easy to collect, such as demographic variables. We find that all of the subjects, all of the samples have the variable in source 1 observed. But source 2 and source 3 might have variables that are hard or expensive to collect, such as the genetics variables. So the variable in these 2 data sources are partially observed. In this graph, the white area refers to the missing value. And the goal of this presentation is to generalize the multiple block-wise imputation approach from the cross-sectional study to the longitudinal study. And here is how this multiple block-wise imputation works. In this graph, the shadow area would refer to the missing value, and our goal is to impute this missing value. The easiest way to impute this missing value in the graph above is to use the complete case. So we use all of the information in pattern 1. However, we can also incorporate sample in pattern 3. But since the variables are partially observed, the variable in pattern the variable in source 2 are not observed for subject in pattern 3. So we can only use the information in source 1 to predict the missing value. And so we have 2 imputation approaches. And let me quickly go through how this method works. So this estimating equation is very similar to generalized estimating equation. However, we approach the working correlation matrix by the sum of basis matrices. And but this AKJ are the nuisance parameter. And we define the extended score vector to avoid estimating this nuisance parameter. And we can obtain extended score across all imputed covariance matrices and sources. But the number of equations exceeds the number of parameters. So we would adopt generalized method of moment to fix this issue. Finally, by adding a penalty term of beta, and we would have an objective function that defined as follows. Here, C beta would be a block diagonal matrix, and the P lambda would be a self-defined penalty function. Here, in this presentation, we use the scatter penalty, and we applied the proposed method in a data analysis. So we have three data sources. This is a census tract level data, and from Michigan. Totally, we have 853 census tracts. The first data source are population level analysis and community estimates. This includes variables like the health information, such as the number of adults with diabetes or the number of adults with asthma. And another data source is national environmental public health tracking. So two air quality variables are obtained from this data source: the PM 2.5 concentration and ozone concentration. And the third data source is American Community Survey. It contains variables regarding to housing, economics, and demographics. We have two time points, 2010 and 2019. The outcome of interest would be number of adults with asthma, number of adults with high blood pressure. We will omit listing all of these variables since totally we have around 17 variables. And the goal of this analysis is to find what are the potential variables that are correlated with the number of adults with asthma or high blood pressure. And also we are highly interested in variable of concentration of PM 2.5 or ozone. So we would ask if our areas with high concentration of PM 2.5 or ozone are more likely to have more adults with asthma. Here is the result or the variable that's highly correlated with these two outcomes. We find that PM 2.5 has a positive association with number of adults with asthma. Also for the number of adults with high blood pressure, the ozone concentration and PM 2.5 concentration are both positive correlated with this high number of adults with high blood pressure. So we may, so I would suggest that for people who want to reduce the risk of asthma or high blood pressure, moving to an area with low PM 2.5 concentration. And regardless of correctness of conclusion, now we should take care of ourselves, have a good management of health, and also taking care of the environment. Thank you.